another pole. Let's make it 3D. So one is north, one is south. And if we have a metal wire, like in between these two north and south pole, and this wire is conducting current. Let's see, we have a current goes this direction is with the magnitude of 13 amps. And the magnitude of the magnetic field can use B represent the direction, and it's pointing from North Pole to South Pole. And if we have this setup with the magnitude of our magnetic field and the current flow into the wire, and the force generated from this magnetic field of this current gonna be, you can use right-hand rule to find that force gonna point into downwards. And the relationship between F current and B can be expressed by the Lorentz force law. And this is a basic rule for all electric motors. It goes forces as a vector equals the length of the wire that is inside of the magnetic field times current as a vector, cross product. You guys learn cross product from statics and dynamics, right? Cross product the magnetic field flux from North Pole to South Pole. And this, so the force generated by this motor, it follows this rule, this equation. And so that's the most basic equation for all the motors. And since the motor is, it generates a rotational motion, right? So what happens if we put a metal wire inside of, instead of just one single wire, we put a kind of a loop in between north and south pole. So if we have north and source, and now we have a loop. And if the center, let's call the center point is O, and the distance from the center to each loop, it's D. And now the force generated in this magnetic field, gonna, one side is pointing to up, one another side pointing to downward. And from what we learned in other mechanical classes, torque, we use T to represent the torque of this metal loop inside of this magnetic field. Torque T gonna equal to, since we have a couple force, right? Force, and then we have a point that this loop is gonna rotating about, and we know the distance, so that we can find out the torque gonna be 2 times dF. That makes sense. That's about 0.0, so I will add. That's about 0.0, torque about 0.0. And what happens if this metal loop and rotates to a certain angle instead of line up like this? Now let's look at another case. If we have an angle, so now our loop becomes something like this. Okay, so now it's at this angle. Our center point O is still there, O. However, now we have an angle, let's call that angle theta. Right now, we still have two couple force. We know the angle and the distance d. Now it's right here. This side here give us distance d. Since the distance from the center to where the metal wire doesn't change. So in this case, how can you find the torque T with this given angle theta? About 0.0. In this new position, our torque gonna be 2 times dF. However, now since we have this angle, and we need to since the torque goes force times distance from the force, perpendicular distance from the force to the center point. So now the distance from the force to the center point O is not d anymore. It's this d times cosine theta. So we have this cosine theta. So the difference between the position 1, position 2 is, and now we have this cosine theta to consider the change of distance, perpendicular distance from the force to the rotation point O. Since as we know, cosine theta is always like less equal to 1. So that tells us at this position, we have the maximum torque, right? Since the torque gonna be just 2dF. However, when this metal loop rotates and that angle increases and our cosine theta will become less than 0, less than 1. And so at this location, this torque is less than the torque at position 1. So if we can plot this, on the vertical direction, going to be torque. On the horizontal direction, going to be angle theta. Let's see. Start from 0 degree all the way to 180 on one side and negative 180 on the other side. And see if our torque gonna be, this is 0 and 1, negative 1. Let's see, this is negative 1 for torque. And if we want to plot how the torque changes with different angle, it's gonna look like something. So something like this. Let's this at 0 torque. I will draw a horizontal line to show that's a line that has 0 torque. So at 90 degrees, both negative 90 and positive 90 degrees, and we have 0 torque. And at 0 degrees, we have the maximum torque, which is 100% of 2dF. And at both negative 180 degrees and positive 180 degrees, we have the negative maximum torque. So as this metal loop rotates inside of this magnetic field, you will see the alternating of torque that changes between positive and negative and 0. And so this is a very, if you design a motor like this is going to be a very bad motor design. Since first the torque would change from positive to negative, negative to positive. That's something we don't want to see. If you have a motor, you want the motor either generate all positive torque or generate all negative torque. You don't want alternating between both. And also we don't want seeing zero torque points in a motor. So this is a very bad motor design. And also this is under, all this we're talking about is under constant current. We assume we only gives constant current to this motor. That means the direction of current keeps the same, right? And magnitude keeps the same. So if the direction of current goes into the loop is the same, when it rotates to a different angle, that's why you get a positive and negative torque, if that makes sense. And this is some like basics about motors. We're gonna go look into this, how to improve this design later. But before we move on, and let's go back to this, the most basic equation for electric motor. Look at this: F equals L times I equals B. And since if we want to have a motor, for example, we want to have a DC motor for a electric go-kart, or you want to build a car, electric car. And in order to improve the performance of the motor, to make it has a large torque, the torque is related to the forces. So from this equation here, we know if we want to increase the torque, the force, and there's several things we can do. Either this L is the length of that wire instead of magnetic field. We can increase the length of that wire, make the motor larger and bigger, right? Another thing is we can use higher current to power the motor. And or you can just use a stronger magnetic field, right? That's 3 different ways you can change the force generated in the electric motor. Okay, so we talk about this very bad design. You have this torque alternating between positive, negative, and zero. And now let's see what are the solutions we can make this the simplest motor better instead of having this negative positive torque. So one thing we can do is, like I said, here we assumed everything is constant current. That's why we see this negative torque there. If we want to get rid of the negative torque, that's one thing you probably thought of is we can switch the direction of current, right? If we can add a switch, we can once it's rotate to the negative 90 degrees, we switch the direction of current, so it will give us positive torque again. Yeah, that's the first thing we can do. It's change color here. First solution we can do is switch the direction of current. And if we do that, then let's draw this again. If this is torque, now we have negative 180, 0, 180 degree. This is 0 torque, 1, negative 1. And our torque gonna change like this. So we'll drop down to 0 at negative 90 degrees. Oops. Then go up, drop down, go up, but it's always above 0. So now if we can switch the direction of current, we're able to generate torque that is all positive. So a little bit better. So now we have all positive torque. But still not very good. As you can see, at both positive and negative 90 degrees, we have 0 torque. That means the motor will be really weak at that particular angle. So what we can do to improve that inconsistent torque output So another way we can do is we can add more wire loops, and for in this case we only have one loop. This is one metal wire loop. If we can add more, like let's see if we can add 3 loops and set them as 120 degrees apart from each other. Then if we can plot the torque and angle again, then we're still gonna have the same plot. I will just do this. We're gonna still have something looks like this. Let's copy this. But instead, now we have 3 different loops. I would use 3 different colors, and they're 120 degrees apart from each other. So it's gonna look like something like this. The second loop gonna generate a torque plot, looks like this. Oops. It's not right. Oops. And we have another loop with a different color that may look like this is not very accurate, but that's kind of give you an idea. If you have more loops, wire loops, and then you will have generate different like various torques at different angles. Even you have one loop that generates 0 torque, but you have another 2 loops that will give you some torque, either maximum torque or half the torque. And so overall, you're gonna get a more consistent torque. So if we draw a resultant torque, gonna be something like this. Gonna have some small ripples, but overall it looks much better than just the electric motor with single wire loop. So that will give you an idea. If you add more loops, metal loops, then wire loops, you're gonna have a more consistent torque output. But still, and you're gonna have small like variations. That if you can add more and more, but that will increase the cost. If you're adding more wire loops in the motor, think about what consequences you're gonna have. First, if you have more wires, you're gonna have more, when current passes through the wires, you're gonna have more ohm loss, right? And that's something you couldn't get rid of. And another thing is you're gonna increase the weight of the motor, increase the cost of the material, and also if you have more loops, and the inductance of the motor is getting higher and higher. Okay. So another thing here, we're talking about just adding more loops, and there are potential problems that like the motor could still suffer from insufficient torque. And if we want to increase torque, we mentioned from the basic equation, we can add a stronger magnetic field or increase the current or increase the length of the wire. Another thing is we can do is, instead of just using loops, we can use coil, right? You coil them together Instead of just using loop, we can do a coil. And we can do multiple loops adding together, become a coil to increase the torque output from the motor. Another thing, problem we may run into is during motor design is how to switch current. Since here we mentioned in the first solution, if we can switch the direction of current and we're able to get all like a consistent torque, either positive or negative torque. But how do we do that? So inside of DC brush motor, and we use commutator and brushes, a set of brushes to do this switch of direction of current. For example, if we have negative and positive, and we have a commutator segment right here and right here. This is, and we can have a coil connected with those two commutators, and each part of this kind of semicircle is called commutator segment. Oops. This one. Usually inside of DC electric motor, you will need at least 3 commutator segments. You need at least 3. Here I only draw 2. This is a much simplified DC motor design, but in reality, you need at least 3 commutator segments. So let me draw a better design. So 3 commutator segments, and they're gonna have 120 degrees each, and each commutator segment is gonna connect with 2 coils. And so let's call this 1, 2, 3, and we have the coil. This is coil B, coil A, and we have another coil connected between this commutator 1, 2. Let's call this C, A, B, C, 1, 2, 3. Okay, and so now we have 3 commutator segments, and brushed DC motor going to have 2 brushes. Brush are usually made from carbon graphite. Brush on one side, and there's going to be another brush on the other side. And the brushes are connected with a power source. And outside the coil and brush, we're going to have 2 magnetic field. S and okay, now we have a very simple design of brushed electric motor. And let's look at the 3 coils inside of this motor at this particular moment. So at this moment, as you can see, the brush on the right-hand side is connected with the commutator segment 2 and 3. Let's make this longer, so make sure 3 is inside of the brush. So make sure you understand the brush and the commutator, they have physical contact. They're conducting current, electric power. And so at this particular moment, 2 and 3 are contacting with the brush here. And if we look at the coil instead of here, let's look at coil B first. Coil B, one end of coil B is connected with the segment 3. Another end of this coil B is connected with this commutator segment 2. Both 2 and 3 are connected with this the same brush, and this brush has the same voltage. So under this, at this moment, at this angle, coil B, it does nothing because is not energized, because both ends connected to the same brush at the same voltage potential, right? So it's not energized. And now let's look at the other two coils. At this moment, coil A, one end of the coil A is connected with this commutator segment 1, and that is connected with the brush on the left-hand side. Another end of coil A is connected with 3, which is connected with brush on the right-hand side. And so at this moment, coil A is energized. Same with coil C. As you can see, one end is connected to 2, another end is connected to 1. They're at 2 different brushes. So at this moment, coil both A and C are energized. So in a real motor design, you can have multiple, much more than 3 coils and more than 3 commutator segments. And this is how brushed DC motor change the position, change the direction of current flow in order to create a positive torque. Okay, now let's keep. Now this is the basics. We know how motor works and we know how to improve the design of a motor. Now let's look at some, what's the mathematic equation we use for brushed DC motor. So next, I'm going to talk about brushed DC motor equation. Oops. So we're going to look at how the electric power, since we know we use electric power to energize a coil and to generate the torque inside of the rotor to make the motor rotates, to generate mechanical forces and power. So we want to look from the perspective of how power is transferred from electric power to mechanical power. So as we know, electric power can be written as current times voltage. That will give you electric power. Let's write it down. And that's the power we input to the motor. And that power equal to, we know you put power into a motor and you see rotation. That's mechanical power. You know we're going to have mechanical power. And that is the in forms of rotation of a shaft. How would you express the power from a rotation motion? So that's going to be torque times omega, which is the angular velocity, angular speed, right? That would give you mechanical power. If this is just the equation, that's all for the equation, and we will have 100% efficiency, right? No matter how much power, electric power input to the motor, you get that much of power as mechanical power. However, this is not possible in reality. In reality, we always have losses. So the equation is still going on here. The electric power is converted to mechanical power plus the power loss, the heat loss in all the wires. So that's I square R. That's the loss in resistance heat. And after this, we still have more loss. Then remember, we put multiple loops together to form a coil, and the coil, it's an inductor. So the energy can be stored inside of inductor, goes E equals 1/2 inductance times I square. And since here in this equation, we're talking about power. So if we can take a derivative of energy with respect to T to find out what is the power loss from the inductor, that would give us L I D current was dt. Oops. So the last term here, it's the power inside of inductor. That is I L D I dt. Do we have other power inside of this equation? Yes, we do. We have more things to need to consider, but we ignore them just for this course, this class. We also have some other terms here, such as friction and others. That's more advanced content for DC motor. But so far, we just need to consider the mechanical power and the losses in the resistance, heat, and the power in inductor. Okay, now we have the most basic brush DC motor equation. And if we can divide the equation by current, then we can write this equation as just voltage on one side. The other side, we have T over I omega plus IR plus IL d I dt. So it's here we just divide current on both sides of equation. Now we end up with a very important parameter for DC motor. This T over I here, it's called the torque constant. That's KT equals T over current. That's torque constant. So that's a constant you will see from data sheet of a given DC motor. And if not in the future, you see torque constant given a certain value, for example, 300, you will know that 300 equals to the torque divided by current. And the unit of that torque constant goes, oops. So on the top we have torque, that's Newton meter. On the bottom we have current, so it's amp. So that's a unit for the torque constant. And also we can write this torque constant in SI unit. That's going to be voltage times second divided by radian. So we can also, if you write have this unit for the torque constant, this is also called electrical constant. But just remember this torque constant, KT equals T over I. It's the most important parameters for DC motor. And you will find that in all different data sheets. Okay, now let's we can rewrite our equation by using the torque constant. So now we have current voltage equals KT omega plus IR plus L di dt. And now if we look at this equation for our DC motor, now if we have, let's look at the condition if we have current equal to 0. So there's no current goes into the DC motor. And under that condition, that's pretty much you have a motor sitting on the desk without connect the motor to any power source, right? That's a open circuit condition. So what happens if you have a motor that is open circuit condition, and this equation gonna, since this open circuit, no current, both the second term and third term where it goes to 0. Right, so let's rewrite this, gonna be V equals just KT times omega. That's under the open circuit condition. And that if we draw our motor here, on the other hand, we have positive and negative. Imagine if you have a motor, if you rotate this shaft with a certain angular velocity, you use your finger to rotate to spin the motor, and if you add a voltmeter on the other end of this motor, you're gonna read some voltage from the voltmeter when you rotate this motor with your fingers, right? And that voltage you will read from the voltage meter gonna be KT times the rotation, the velocity, omega. So in under this condition, this motor is acting as a generator to generate power, to convert mechanical power to electric power. And so that tells you a motor can be work in either ways, either generating mechanical power to electric power, or generate use electric power to generate mechanical power. And if you have a motor, you don't know the torque constant, you can use this to estimate what's the torque constant by giving a certain rotation, if you know the angular velocity, and you can also measure what's the voltage rating from the terminals in between the motor. And after measuring several points, you were able to find what is the kind of the plot for what's the value, estimate value for the torque constant. And sometimes we call this torque constant times omega as back EMF. Sometimes if you see back EMF, that just means the times the product between KT and omega. And that EMF just means electromagnetic field. Okay. That's the introduction of the brushed DC motor equation. And now you should know there are three very important terms inside of the brushed DC motor equation. And first two is the torque constant times omega, and that's also called back EMF. And the second term here we have IR. If we go back to the original form of the equation, that comes from I squared R. That's losses in all the wires. And now we also have a power term, the power instead of inductor. Okay. And with knowing this DC equation, DC motor equation, next thing we're going to talk about another very important thing for motor, that is the speed torque curve. So usually if you look up, you want to buy a DC motor and you are able to find what is the kind of speed torque curve on the data sheet of the website will probably give you. And here, when we look at the speed torque sheet, we want to look at what's this curve look like under a steady state when current is constant. And current is constant. Then let's go back to our equation. V equals KT omega plus IR plus L di dt. If current is constant, and what term will goes to zero? If you look at the third term, di over dt, that's how current change. If current is constant, then this third term would be zero. And also we're going to look at how this, how the curve looks like under a constant voltage. And so if that term is zero, it will only left with this two term, these three terms, V, KT, W, omega, IR. And can we write an expression just for omega, since we want to know how fast, what's the speed of motor related to the torque. So we can rewrite this as omega equals 1 over KT V minus R KT square T. Okay, so that simply just put omega on one side of the equation and throw everything else to the other side of the equation, and by using the torque constant and to convert one of the to have a torque inside of the equation would be handy. And so if we look at this expression here, and under constant voltage, since we always want to run our motor in a constant voltage, if that is voltage constant, this term goes to constant. That doesn't change. So that only left with omega, which is the angular velocity, and this r over kt squared times torque term. And this is a constant, r is a constant. So we left with a relationship between omega and torque. And that's where the torque constant comes from. So we can draw the vertical direction as omega with the unit radian per second. On the horizontal direction, we have torque, Newton meter. And the torque's speed torque curve gonna be just a straight line under a constant voltage. So at the top of this line, right there, when we have the maximum omega, that's the no load speed. We call that point omega O, no load speed. That equals V over KT. So that's a maximum rotation speed you can get from this DC motor. And when there's no load. And on the bottom here, we have the one point that has zero speed, zero velocity. That will give you the maximum torque. And that's also called stall torque. That's the situation when the motor is running, you use your finger to hold the motor. So you force it to stop. So that's a stall torque. And that equals KT V over R. And just be careful, this is a very bad point to run the motor at the stall torque, since omega is going to be equal to 0, and that means all the current goes into the motor will not convert to mechanical power. Instead, all the current will generating heat. So if you're running at that point for a long time, you're going to burn and damage your motor. So, and basically this is just a speed torque curve gonna look like under a given voltage. So under different voltage, and you're gonna see the curve like have opposite, they're gonna look like this. Of smaller current, the curve, the line gonna getting close to the origin point. Let's call this 0. And what other things? So here, usually in the speed curve, we define the region, this region here, let's call this 1, 2. So we call that point there the nominal operating point. So that's kind of the suggested operating point for the motor. And under the constant voltage, this point also give you the nominal mechanical power. And the corresponding omega here, it's the nominal angular speed, omega. That's the corresponding speed. And the corresponding torque is T nominal torque. So that's the, if you look at the data sheet of DC motor, when you see nominal speed, nominal torque, and they're not the torque, the maximum or the minimum torque of speed, they means the torque at that point. And So like also I labeled 1 and 2, and the region 1, it's called continuous operating region. So that's a region you can continuously run your motor without damage your motor. And the other regions are called the region 2 specifically. It's called intermittent operating region. So at region 2, that's the region you can run the motor for a short time, but not continuously. If you continuously run the motor in region 2, and you're running the risk of burning your motor. And at that point where the motor provides the maximum torque, the stored torque, and that's also the point motor will require the maximum current flow, has a maximum current flow into the motor. And so remember, that's not a good place to run the motor, especially at that point. So now you should able, when people talk about torque, speed torque curve, and this is how speed torque curve look like. Okay. All right, and that's a lot of contents about motor. And how about let's take a 5 minutes break and let's come back to this.